Okay, welcome to the concurrency session of POPL. Before we begin, I've been asked to tell that these two exits can be used to go on a break, so there is no need for everyone to go upstairs. There's plenty of room here. So the first talk is immediately going to attack one of the most pressing problems in the field of concurrency reasoning, namely specifying the behavior of modern multiprocessors. And for the past 6 or 7 years, this topic has been making a regular appearance at POPL with a lot of interest from the community. Many solutions have been proposed, and Jeehoon is going to show a promising new one. So, please.
Can you hear me? Okay. Thank you. My name is Jeehoon Kang, and today I'm going to tell you about one of the major open problems in the study of relaxed memory concurrency and a very promising proposal for how to solve it. First things first, what is relaxed memory concurrency? Well, for the past 10 years, a lot of people have been trying to figure out how to define the semantics of multi-threaded programs, but this has proven to be a very difficult task. The simplest answer is to use sequential consistency, or SC semantics, in which there is a single global memory and threads take turns reading or writing to the global memory. Unfortunately, although SC is appealingly simple, it is also very expensive to implement, because parallel architectures do not have a single global memory, and to pretend they do, compilers need to add a lot of synchronization between cores. So instead, people have tried to develop memory models, typically called relaxed memory models, that gives programmers SC semantics when they need it, but also allow them to use cheaper and less weakly consistent atomics when they don't. This is the essence of the C++ and Java memory models, which provide us thermal consistency modes for programs to use depending on their needs. It turns out to be very difficult, however, to get these relaxed memory models to do the right thing. What do I mean by the right thing? Well, a relaxed memory model really has to serve 3 different masters, namely compilers, hardware, and programmers. And as you may guess, these masters have conflicting goals. On the one hand, for compiler and hardware, the semantics should validate optimizations that are actually performed in the real hardware and compilers. For example, the semantics should account for the instruction reordering due to out-of-order execution, merging, or other optimizations that are performed by hardware caches or compilers. On the other hand, for programmers, semantics should support useful reasoning principles. One of the desired reasoning principles is the data race freedom guarantee, also known as the Dreyer theorem, which says that a program without AC accesses has a sequentially constant semantics. In addition to the Dreyer theorem, we want to be able to support the development of a whole stack program logics of reasoning about programs. Unfortunately, all the existing proposals for concurrency semantics fail to satisfy at least one of the criteria. In the case of Java, the memory model does not validate optimizations that are actually performed by the Java reference compiler. In the case of C and C++, their model failed to support useful reasoning principles. Even basic invariant-based reasoning is unsound in C++ due to a major output problem with the model, known as the out-of-thin-air problem. So let me now explain to you what is this out-of-thin-air problem and why is it so hard to solve. To understand the problem, let's start with an example, which is known as the load buffering example. Here, suppose that lowercase a and b denote thread local registers, and the uppercase x and y denote shared memory locations, which are initially set to 0. In addition, all the accesses in this example are relaxed accesses in the C++ terminology, which means that they should be compiled down to plain loads and stores in the hardware without any added synchronization. So in this example, thread 1 loads from x and then stores the loaded value in y. On the other hand, thread 2 loads from y and then stores the number 42 to x. The question is, should we be able to observe that a and b are both 42? At first glance, it may seem surprising that the behavior should be allowed, but indeed it should be allowed because the power and architectures may buffer load instructions with the effect of reordering the instructions in thread 2. In a reordered program, it is possible to observe A equals B equals 42 on a normal sequential constant execution. Okay, so what I have just gave you is an operational intuition for how this behavior can be observed in weak architectures. But C++ memory model is not characterized in such an operational way. Rather, C++ is defined in a declarative axiomatic style in which a program execution is represented as an event graph, which describes the history of the memory accesses during the execution and the dependencies between them. The execution is considered valid or justified if the associated event graph satisfies a certain set of actions. The load buffering behavior A equals B equals 42 is allowed because it results from the execution depicted here on the right-hand side of the slide. So far, so good. But the problem with the C++ axiomatic semantics is that it justifies too many graphs, and thus it allows too many behaviors. To see an example of this, let's consider the following variation of the previous example, where instead of x equals 42, we have x equals b. Now again, let me ask the same question. Should we be able to observe a equals b equals 42? And this time, the answer is, let's hope not. If this behavior were observable, it will literally out of thin air, since 42 appears nowhere in the program. Furthermore, it would break all manners of reasoning principles, all manners of reasoning principles one could hope to have. In particular, it would break basic invariant-based reasoning, asserting that x and y are both 0 throughout the execution of the program. However, surprisingly, C++ allows this behavior. Without going into all the gory details, the reason C++ allows this behavior is that the same graph this uses to justify load buffering behavior from the previous slide can be also used to justify this out-of-thin-air behavior. This implies that C++'s axiomatic semantics allows too many behaviors and brings useful reasoning principles. This problem is called out-of-thin-air problem. So how can you attempt to solve this problem? Well, a nature science point to understand is what hardware models do distinguish this load buffering example and out-of-thin-air example, because it properly distinguishes these two examples. The way that hardware models distinguish these two examples is by tracking syntactic dependencies between instructions. On the left side, in thread 2, b equals y and x equals 42 are independent from each other. On the other hand, on the right-hand side, there's a syntactic dependency between b equals y and x equals b. Hardware models recognize this difference so that they can allow the load buffering behavior in the left while forbidding the out-of-thin-air behavior in the right. But unfortunately, this approach does not work for programming languages. To see why, consider the following variation of the load buffering example. In this variant, presented in the left, we have inserted a false syntactic dependency in thread 2 by replacing x equals 42 by x equals b plus 42 minus b. Now the behavior is forbidden in hardware because there is a syntactic dependency between the two instructions in thread 2. However, for programming languages, the two instructions the example should be treated as the same as the original load buffering example, because compiler may optimize b plus 42 minus b into just 42, thus removing the syntactic dependency in thread 2. Indeed, this behavior is allowed in C and C++, and it should be allowed. So the lesson learned here is that syntactic dependency approach is fine for hardware, but it doesn't account for compile optimizations, and therefore does not solve the out-of-thin-air problem for programming languages. Actually, this problem has turned out to be infamously difficult to solve, and a paper in ESOP 2015, Betty et al. Described it as a major open problem for programming language semantics. Okay. In this paper, we present a very promising semantics for relaxed memory concurrency that provides a more comprehensive solution to the out-of-thin-air problem than any proposed before. As we will show shortly, the phrase promising semantics here has a double meaning. Our promising semantics is comprehensive in that, first of all, it validates compiler and hardware optimizations and supports useful reasoning principles at the same time. Also, our promising semantics cover most of the concurrency features in C and C++. The promising semantics is an operational semantics, and unlike C and C++, it does not rely on undefined behavior to define the semantics of racy programs. Undefined behavior may be okay for languages like C and C++, but we also want to develop models for languages like Java, in which old well-typed programs should have well-defined behavior, so it was important for us to not rely on undefined behavior. Finally, we formally verified most of our technical results in the Cox theorem prover, and I will tell you more about those at the end of the talk. Now, as I said, promise semantics has a double meaning. First of all, we think that any semantics that does all things listed here is pretty promising. In addition, the key idea behind our promising semantics is the idea of promises or promised rights. A promise is a way to make a right visible to other threads before it actually occurs, and this is essentially what is necessary to explain the observed behavior in the load buffering example. More precisely, in our promising semantics, a thread can promise to write x equals v in the future, after which other threads can read the promise write x equals v. But as I explained, we should be able to distinguish load buffering and out-of-thin-air examples, so we have to only reliable promises. Therefore, in order for a thread to promise to write x equals v, it must certify that it can actually write x equals v in isolation. Let's see how this works with the motivating examples. First, for the load buffering example, even though thread 2 did not load from y yet, it can promise to write x equals 42. This is because thread 2 can certify that it can write x equals 42 in the future without any help from thread 1. Then thread 1 can read 42 from the promised write, and then write 42 to y, which can be read by thread 2. Lastly, thread 2 can keep the promise by actually writing 42 to x. Now let's introduce a false syntactic dependency by replacing x equals 42 by x equals b plus 42 minus b. Even in this case, thread 2 still can certify to write x equals 42 in isolation, so the same execution works, and the same behavior is observable. On the other hand, in the out-of-thin-air example, thread 2 cannot certify to write x equals 42 in isolation, so it cannot promise to write x equals 42. Therefore, the behavior is not observable in this example. So far, I explained how promises explain variations of the load buffering example. At the high level, it works because the promise is a semantic solution to the out-of-thin-air problem, and it's not tracking syntactic dependencies. Okay, now in the rest of the talk, I will explain some more details of promising semantics. First of all, let me talk about the style of semantics we use, because our promising semantics is very different from C++'s declarative event graph semantics. Instead, we use an interleaving operational semantics. In this respect, our promising semantics is much like sequential consistency, except that the machine state in our promising semantics is not a file memory mapping locations to values, but rather it is a message pool where each message corresponds to a write event in the program. A message records three things: a location, a value returned to that location, and the timestamp of that location. that write. Furthermore, each thread has a view on the memory, which picks a message for each location. For example, here, thread 1's view picks a message for x with a value 0, and one for y with a value 42. A value determines what a thread can do. When a thread performs a read from location x, it's free to read any message for x whose timestamp is at least as big as the one in the view. When a thread performs a write to location x, it must choose a timestamp greater than the one it has recorded for x in each view. But different threads may have different views on the memory, and so with views, you can easily explain one of the most canonical with memory examples, the total buffering examples. Recall that A and B are registers, and X and Y are shared locations that are initially set to 0. Here, thread 1 stores 42 to Y, and then loads from X. On the other hand, thread 2 stores 42 to X, and then loads from Y. The question is, should we be able to observe that A and B are both 0? The answer is it should be allowed, because CPUs may locally buffer the stores, so that at the point when those instructions occur, those stores have not yet been flushed to the memory. Now let's see how we can explain this store buffering example with views. Thread 1 may write 42 to Y, moving thread 1's view on Y. Then thread 2 may write 42 to X, moving thread 2's view on X. Now, thread 1 can read the 0 from X, because its view on X points to the message with value 0. And the view is not changed because the view is already on the read message. Likewise, thread 2 can read 0 from y because its view on y is point to the message with value 0. Similarly, the view is not changed because the view is already on the read message. Now let's return to our old friend, the load buffering example. In this example, promises play a key role. Recall that in order to explain the load buffering behavior, thread 2 should promise to write x equals 42. But in order to make a promise, thread 2 must certify that it can actually write x equals 42 in isolation without any help from thread 1. So we focus on thread 2 and check if it can write x equals 42 in the future. It is indeed the case because it can read y equals 0 and then write x equals 42. So the promise is certified. Now let's go back to the normal execution after the promise step. Now thread 1 may read 42 from the promise write to x, increasing its view on x to 42. Thread 1 can read 42 to y, increasing its view on y to 42. Then thread 2 can read 42 from y, increasing its view on y to 42. And finally, thread 2 can keep a promise by actually writing 42 to x. Now let's see what happens in the case of the false syntactic dependency. Still, thread 2 can promise to write x equals 42 because, as in the original load buffering example, thread 2 can write x equals 42 in isolation, so that you can easily see that the same execution works for the same reason. Okay, so far I explained load buffering behavior with promises. Now, what about the out of thin air example? Then thread 2 cannot make the promise because it cannot write 42 to x in isolation. The only value it can write to x in isolation is 0, so the thread 2 must be 0 from x and y, and a and b must be 0 as well. As I said earlier, in essence, promises explain all the variations of load buffering examples, because it is a semantic solution to the out of thin air problem, as opposed to the previous solution based on syntactic dependencies. Okay, now let me summarize the results of our paper. We propose the promising semantics for relaxed memory concurrency that solves the out of thin air problem. In the paper, we provide a lot of formal evidence that the promising semantics is more comprehensive than any prior proposals. First of all, the promising semantics is an optional semantics with an undefined behavior that covers most of the C++ concurrency features. More precisely, our model supports plain or non-atomic, relaxed, release, acquire XMOs for load, store, update, or modify write, and fence operations. It also supports SC fences. This is basically everything in C++ except for consume and SC accesses. Furthermore, it validates many compiler and hardware optimizations. In particular, we formally verified the soundness of many instruction reorderings and merges, as well as dead code elimination in the Cox prover. Also, we proved compilation correctness to x86 and power. In particular, the x86 result is proved in Cox. In addition, we provide useful reasoning principles for the promise semantics. We proved the Dreyer theorem, which says that if a program is well synchronized, meaning that it only raises an x-axis to loss, then it has a sequentially constant semantics. In course of proving DRF, we formally verified what we call promise-free DRF, which says that for well-synchronized programs, promises introduce no additional behavior. Because promises are the most complicated part of our semantics, it is the key lemma for the Dreyer theorem. We also formally verified the soundness of a simple program logic based on a global invariant, which says that if an invariant is preserved by every execution, every instruction in the program, then it actually holds throughout the execution. In one sentence, we proposed an operation semantics for C and C++ concurrency that is more comprehensive than any prior proposals. You can find the development in our website. To conclude, let me mention some directions for future work. First of all, you may find it suspicious that our model does not support sequentially constant or SC reads and writes, since they seem too easy to support. But actually, it turned out that getting SC semantic correct is much more complicated when SC is used concurrently with other consistency modes. In fact, in course of doing this work, we uncovered a flaw in the C++ memory model concerning SC accesses in that the widely accepted compilation schemes power architecture are broken. So clearing of the semantics of SC accesses is an important problem for future work. Another important future work is supporting the C and C++ consume semantics, which is intended to model a low-cost synchronization that is used heavily in the Linux kernel. Furthermore, we'd like to prove that our promising semantics can be soundly compiled to ARM v8. We strongly believe that there are no counterexamples. Lastly, we'd like to develop a much richer program logic than the one we presented in the paper, which is a logic in which we can verify realistic fine-grained concurrent programs, such as lock-free queues or garbage collectors. So thank you for the listening.
Hello, I'm Patrick Couzeau. I have a problem with your reasoning in isolation because the value 42 could come from other processors, and the fact that you are able to write it might depend on the fairness hypothesis on your program, and you never spoke about that.
Would you please repeat your question, please?
In which language?
The last part.
Okay, so you reason in isolation, prove in your example that one process can write 42. But this 42 was local to the process. In general, it will come from interaction with other processors.
Yes, yes.
And this interaction may be in loops, and the fact that ultimately some value will be written might depend on fairness hypothesis that you have on the processors, including strong fairness, if you have semaphores or things like that.
Okay.
In your case, you never spoke about fairness and this problem, so this is my question. What do you do about this case?
Okay, basically, we want to conservatively model the interference so that we just assume that other threads can do anything possible in semantics. So looping over is one example. So in fact, we require that the promise thread can certify the promise right even in any interference of other threads. So that's the detail I didn't present in this talk, but it is in the paper. Basically, promising semantics is not intended to be implemented. So we proved the compilation results to x86 and other architectures so that we can run on the architectures.
Thank you for a very nice talk. Could I get you to go to the example of page 7 so I can ask the question a little more quickly? So I'm trying to understand the practical impact of the very elegant semantic compared to the syntactic restriction. So you said, in conclusion, we have to support this behavior, we have to allow this behavior, even though it's not clear whether there's a syntactic dependency. Could you tell us why you have to allow it? Why not have a strategy that if you can establish syntactic dependency, then you allow it. If you cannot, then you conservatively don't allow it. What's the useful optimization we're missing by just conservatively not allowing it when we're not sure there is a syntactic dependency? Okay,
so suppose that this B here, this X here is basically B here is a register. So this is really perfectly saying to optimize B plus 42 minus B into 42, I think, in full compilers. It's registers and it is nothing to do with shared locations. So compilers really do the optimization, I think.
But the motivation for handling this in the first place, that the hardware is going to allow it, the hardware allows. If the hardware cannot establish syntactic dependency, it will not allow it. So in practice, what am I missing by being conservative? Maybe we can take it offline. And what will happen? So if you raise it, what would be the right behavior then?
So
which, okay.
So basically, compiler will happily do this optimization because B is a register, it is not your location or it is not access memory. So it is what compiler does, and if we admit that it is reality, then I think it is mandatory. We are required to allow this behavior in program languages level. So,
Okay, so the last question from there.
Hello, thank you for this talk. My question is, if a program was proven correct with respect to the current version of C11, is it still correct in your semantics? Do you have a result that relates your semantics to the current one?
Would you please repeat your question, please?
If a program was proven correct with respect to the current C11 semantics, is it still correct with yours?
So you're basically asking the relation between the C11 semantics and this semantics, right?
Yes, exactly.
So we proved an equivalence result with promise-free semantics without promises in our paper, and some axiomatic graph semantics. So it is not equivalent to C11 because it does not allow load buffering behavior, but basically we proved some relation with our semantic to some C11 size semantics, but it even though it doesn't say conclusively about the relation to C11, but I think it will give you some more insight on the relation. So maybe you can take it to offline to discuss more. Thank you.